trigonometric identities. Basically, what we're going to be doing here is that we're going to be rewriting and simplifying trig expressions in multiple different ways. We're going to try and simplify things out as much as possible. It may look a little weird to start with, but as you get the hang of it, bless you, it really isn't that bad. Basically, you get these, and you know, you know your reciprocals. Oops, this is a little. You know your reciprocal. You know that cosecant is 1 over sine. You know that secant is 1 over cosine. You know that cotangent is 1 over tangent. We know those. It's the inverses. Okay. Excuse me. We also know that tangent is what over what? Tangent.
Opposite over.
Let's think of it in terms of sines and cosines. Remember tangent, when we wrote it out, was sine over cosine?
Oh, yeah.
Have you guys noticed one thing that I leave out a lot? Theta, x. Is it the end of the world?
Probably.
It really isn't. Don't worry if you don't write it out, if you don't put a theta in there, if you just write cosecant as 1 over sine or tangent sine over cosine, I'm fine with that. I forget it usually, so that's why I do that. And then cotangent is cosine over sine. Everybody agree on that? Now, those are, I thought we had 6, I was wrong. Those were 5 that you already knew. Those weren't any new to you. We already knew all those things from earlier in this chapter.
So cotangent equals both 1 over tangent and cosine over sine?
Yes. Yeah. Yep. The new one is the Pythagorean. What happens here is you get sine squared plus cosine squared equals 1.
Tangent.
It equals 1. And then you get the other 2 off of that. And Mom, I was showing you how you can derive those other 2 from just knowing that one before break. You're asking about that. So what's happening here is if you want to bring it back to the unit circle to prove how this stuff works out, you wind up showing that you can get the Pythagorean theorem off of your sines and cosines by drawing out the right triangle, and you're always going to get that radius of 1 of the unit circle to go around to those points. That's where they're getting that. Okay, remember, when you're on the unit circle, the sine value, your cosine value, that gave you your radius. The radius was always 1. That's how that worked. Excuse me, cosine was that direction, the x direction. Sine was the y. That's how these things work. Now, what Mamer was talking about last week are these other 2. The other 2 look a little bit weird via the Pythagorean identities. What's happening here in order to show that you can get this 1 plus tangent squared is secant squared, or 1 plus cotangent squared is cosecant squared, is the following. If I start with my standard sine squared plus cosine squared equals 1, if I divide everything by sine squared, did I keep it balanced on both sides of the equation?
Yes.
What's sine squared divided by sine squared?
Cosine. No.
1.
Cosecant.
What is when you divide something by itself is always 1, no matter what it is.
I was thinking about the 1.
Cosine over sine is cotangent. It just so happens to be cotangent squared. And what's 1 over sine squared?
Cosecant.
Squared. Okay? So it's very easy to manipulate sine squared plus cosine squared to get the other 2. Now to get the other one, what would I divide both sides by? If I divide both sides by sine squared, if I do it again, if I divide everything by cosine squared, What's sine over cosine? Tangent. So you get tangent squared plus 1 is secant squared. It's the same thing as that. So, like I said, you're probably never going to have to memorize those last two, that 1 plus tangent squared is secant squared, 1 plus cotangent squared is cosecant squared. But if you remember sine squared and cosine squared equals 1, you can very easily manipulate it to get the other two. The trick here is, guys, you know all of your inverses. You know that tangent is sine over cosine. As long as you remember sine squared plus cosine squared is 1, when you take any quiz or a test, you write it down, just divide it out, and it gives you the other two real quick. Right? So there's really only one new thing we're working on today. What this allows us to be able to do, like I was saying earlier, is just simplify some statements, some algebraic trigonometric statements. Like the following. I'll come back to this one. If I take cotangent times secant, and I want to simplify that. Again, don't worry about writing the value of x or anything like that. It's not the end-all, be-all here. What is another way of rewriting cotangent? What, you're right, you could write it as 1 over tangent, but can I break this down as something different? I can write it as cosine over sine. Okay? What's secant? What happens? Cosines drop, and you get 1 over sine, which is? Again, what we're doing here is we're manipulating. Think of it as like a factoring. It's kind of like a factoring problem, trying to see what drops out to rewrite something. You're getting like GCFs and things like that. Now, if you wrote it as 1 over tangent, you would have found yourself not getting anywhere with that right away. And then you'd go back and try a different method. It's very similar in the ideas when you guys were doing proofs last year. If one way didn't work, you had to start over. Excuse me. When I'm looking at sine of x times that jump, well, let's rewrite those other two out so we don't have to keep simplifying. It was 1 plus tangent squared was secant squared. And then 1 plus cotangent squared was cosecant squared. Everybody okay with that? So when I see sine times 1 plus cotangent squared, what can I rewrite 1 plus cotangent squared as?
Cosecant squared.
I can rewrite it as cosecant squared. Or what else could I do? What does this mean when you have something out in front of jump? You could distribute. Let me show you two ways of doing this. So this would be sine times cosecant squared. Cosecant squared is 1 over what? Yeah. So I could rewrite that as sine over sine squared. Everybody okay with that? Remember, how did I get cosecant?
Oh, yeah.
I'm using the identity. I'm using one of those identities. What simplifies?
Or 1 over x squared.
No, because this is, how many sines do we have down here? Sine squared is sine times sine.
Oh, yeah. Then what about the x's that are involved?
It's just like theta. As long as they're the same, you do
all
all
the
the
stuff.
Yeah, it's always. It's at some angle. It's just an awful habit of mine not to write it because it doesn't make any difference.
Okay.
If you don't write it, I'm not going to care. Okay, it's not that, and it's not the only one. Yes, sir. No, there's no solving. There's not solving for x. There's no equations here yet. Yeah.
How would you do it if you
I'm going to show you. If I went to distribute it, it would be basically kind of the same idea. I get sine plus sine. Now, what I'm going to do with cotangent squared is cosine squared over sine squared. Do you agree? All right. Now, again, what's going to happen here is you get sine plus, this would be a cosine squared over a sine. You're kind of stuck, aren't you? When you're stuck, that means there's an easier way to do it. We will get to this point of being stuck probably tomorrow. I'm going to show you another trick. Because how do you add fractions? What do you have to have? You work with a common denominator to get rid of that. So if you get to the point where you do distribute this out, this is why I wanted to show what happens. If you get to the point where you start getting stuck, that means there's probably an easier way. Okay? It's a little bit of it's one of those choose your own adventure type style of books where you shows you just got eaten by a shark.
Oh, I hated those.
Yeah, I hated those too.
I always read ahead and then I always found them that I liked and I always tried
Now you get to do some fun stuff like this. Sine of b over the tangent of b is cos b. See? Little cos b.
No.
Thank you. No? Stretchy? That big stretch here?
it. Yeah.
See? Get it? Sine of b. What can you rewrite tangent as?
Sine over cosine. So it'd be sine of b over.
Does everybody agree that I could rewrite this as sine? I'm going to keep the b in here to make it funny. So this is divided by the tangent of b. Tangent of b would be what do you do when you divide it by fraction? So the sine of b cosine of b over sine of b. So you get cos b.
That's fast.
I love this joke. That's fantastic. No? No. It's from the internet. I hear they have it on computers now. I love this. There's other funny ones, and I'll bring them in eventually. Oh, we're not going to do negative stuff. What is different now? What do you see?
Numbers.
An equal sign. When you see an equal sign, it means you're going to do what's called verify. Verify means you should get this to equal 1. If you don't, you did something wrong. It's telling you what it's going to simplify to. You just need to show how it gets there. Okay? So again, you have cosine times secant. Well, what is secant? 1 over cosine. So what happens here is in order to verify that this actually works, is you would just write out the following. Cosine times 1 over cosine equals 1. And that's a verify. It's telling you your given and your proof statement. Fill in the junk in between. It's telling you what your answer will be in the end. It's just, you need to remember what are your inverses. Same thing with that next one. Tangent, cosecant, cosine, you want it to equal 1. So anytime, there's a kind of a trick here. Anytime you're given a tangent or a cotangent, write it as sines and cosines. Anytime you're given an inverse, write it as a sine or a cosine. Try to bring it back down to the main two, sine and cosine, if possible. Because then you'll start to see things drop out real fast. So what's tangent? Sine over cosine. Cosecant, 1 over sine. And then just cosine. Dun dun dun. And you verify. Again, this is very similar to the factoring and foiling when you had to make it equal to something, or very similar to the geometric proofs that you guys did last year where it told you what to start with, what to end with. How does it work in the middle? Instead of using all those statements and reasons, what you're using here are those 7 basic properties there. Right? It does get real messy, I'm not going to lie to you. This is just, I want to start with this stuff real slow. We'll probably do this for a few days. If I'm not mistaken, I think there's only 2 sections left in this chapter, 14.3 and 14.4. We won't test this week, but we'll definitely test out of this stuff next week. Right? April's really weird. There's not a lot of school days. This week is a full week. Next week is a 4.5 day. And then the following week is 2.5. Following week is 4. And then there's a 5 day. So there's not a lot of school in April. I know you're very heartbroken.
Yay.
You'll get over it. It's okay. Now is when it gets interesting. Yes, sir.
We took the test on chapter 4. We're gonna have to do something.
I haven't quite decided yet. You guys did really well on the graphs. I think what I'll do with that would probably be ask you to write equations that are shifted. Just write the equations from a parent, and I'll tell you what the shift would be or something along those lines. So what's different now?
We don't have numbers.
We don't have numbers, but does everybody see how it goes from a division problem into a subtraction problem? This is where things start to get a little messy.
Oh.
Things can get a little messy here. Again, what I want to do is I'm going to rewrite as much of this as I can to make my life easier. Yeah, it's a lot of complex fractions or rewriting things out by reciprocals and stuff like that. If I take a look at what I have right now, the numerator says cotangent squared. Everybody agree with that? Now, cotangent squared, it's cosecant squared minus 1. Everybody agree on that? What you're doing here is you can move the 1 over to get cotangent squared equal to cosecant squared minus 1. You use some of those adding and subtracting and move stuff back and forth. Again, you can do the same thing with cosine squared would be 1 minus sine squared. Sine squared would be 1 minus cosine squared, just by moving sine and cosine to the other sides. So here I could get, and my numerator then would be cosecant squared minus 1 all over cosecant. Yes, sir?
Before we leave, what's the homework?
Oh, I'll get that out here in a second. That's right, you guys are taking off. Cotangent, remember how 1 plus cotangent squared is cosecant squared?
Yeah.
So what I did is I just moved, I got cotangent squared by itself.
Oh, so you just subtracted.
Yeah. Let's see here. Continue here. So what we've done here, guys, is we've just basically rewrote that in terms of cosecants. Now, notice in your numerator you've got 2 parts, all divided by the same thing. That means I can break that up into this.
Oh, and that's how
Since it has the same denominator, you can break it apart like that. When it's in the when you only have one part of the denominator, you can break it into the 2 pieces because it's the common denominator. Okay? So cosecant squared over cosecant is just old, plain old boring. Cosecant. And that's how that works. Again, what you're doing here is that you're just taking it and rewriting it, breaking it into the fraction and going for it. All right. Yes, sir.
So then wouldn't that just be cosecant minus sine?
No, you're done. You verified it. Remember, it's telling you where you started with and what you have to end with. You just ended with what you were supposed to end with.
Yeah.
Yeah, you're done. That's all it is. Again, the whole idea here is taking the cotangent squared to rewrite it as cosecant squared minus the 1. When you divide it by the cosecant on both terms, you rewrite it as the two separate fractions, simplify both fractions, and you're done. Okay? It's messy.
So you can just bring in the one like that.
Well, I didn't just bring it in like that. What I did is I used the identity where it was 1 plus cotangent squared is cosecant squared. What I did is just got cotangent by itself. That's all I did. Okay, so I just verified, I just moved it around.
Oh.
Does that make sense? And it works,
I
it works.
thought it said cosecant on the top and verified part.
Oh, yeah.
I just read it wrong.
Yeah, it's Monday, you had a couple of days off, it happens.
Yeah. Darn those weekends.
Darn those weekends. Another verify.
Well, wouldn't you just, because it's the reciprocal? I don't know.
You inverse it, right?
Can't inverse something here.
You flip, you times it by itself.
Think about what you guys did to denominators when the denominators were nasty.
Okay.
What'd you multiply by?
You know,
What else?
Within cross multiply.
No, we're not doing a cross. If we're doing a cross multiply, that means we're trying to solve something. If I'm going to verify something, I need to. What I'm basically doing is my answer has to look like on the right, starting with the left. Think about this. What did you do when you had something in the denominator that looked like this? What did you have to do?
multiply the top and bottom by your
We'll just
Oh, it's, oh, there's no, okay. I thought it was.
What would you have to multiply the top and bottom by to get rid of that 2 minus root 3? What's that? Nope.
Plus root
You have to multiply by its conjugate. Remember, you have to multiply it by 2 plus root 3, the top and bottom. That allowed you to get rid of the square root in the denominator, because you wind up with 2 plus, or 2 root 3 minus 2 root 3. The roots would go away. Root 3 times root 3 would give me root 9, which was 3. So that's how you got rid of that. You're basically doing the same thing whenever you see a 1 minus a cosine, 1 plus a cosine, 1 minus a sine, or something like that, that is not already squared. It's not one of the Pythagorean identities. You are going to create it, which means you multiply by a conjugate. So we have sine of x, the x is in, sorry, 1 minus cosine. I'm going to multiply top and bottom by 1 plus cosine. Okay? In that denominator, what you're doing is you are creating one of the Pythagorean identities. When you FOIL out 1 minus cosine, 1 plus cosine, you would get, I'm going to do it the long form, 1 minus cosine plus cosine minus cosine squared. Does everybody agree with that? If I'm foiling that out, I get 1 times 1, 1 times cosine,
Oh, yeah.
minus 1 times cosine, minus cosine squared. What happens to that middle term? It drops, and you wind up with basically 1 minus cosine squared, which is what? Sine squared. Very good. So I know by multiplying by the conjugate on the bottom here, I get sine squared when I do all of that. I haven't FOILed out the numerator yet. I'm getting there. Excuse me. So here I have sine times 1 plus cosine. Again, do I need to distribute that? Exactly. Again, if I distributed that, I would be okay, but I'd have to do a little bit more work later on. But by leaving it, noticing that I have a sine in the numerator and a sine squared in the denominator, and I'm done. I get 1 plus cosine over sine. They're nasty. They can get pretty weird, okay? They can get pretty weird. But then again, in times, they get really easy once you pick up on some of the little tricks within the Pythagoreans. Okay? It's all right. I know, it's nothing better than starting something that's really nasty the first day back.
I think there's a party now that Jim's going on.
Says that.
Yeah, those guys are a bunch of jerks.
Oh, that's it. They're not here, we can talk about it.
We can talk about them if they were here anyway.
Yeah, but then they were gonna watch the video and be like, oh, those some jerks.
Oh, sure. Oh, wait a minute, we can go back to that race.
Oh, sorry, yeah.
I do a race stuff.
Which were you at?
Oh, okay.
Did you see it? With the sign of the sine squared? Try that one. When you FOIL the numerator, you get secant squared minus 1 over tangent. What's secant squared minus 1? Tangent squared over tangent is? I'll get real nasty with this stuff.
I'd rather do
I'll show you.
that. Rather do
Come on, this is fun. Secant squared plus cosecant squared, you want to verify that it equals secant squared times cosecant squared.
Okay.
Yes, you can.
It's not possible.
Yes, it is.
Is it just equal 1 over 1 equals 1?
What is secant squared? All right. This is 1 over
Cosine.
cosine squared.
And the other one would be sine, 1 over sine squared.
Everybody okay with that?
And for the other one.
In order to add fractions, what do they have to have? What would the common denominator be with cosine squared and sine squared?
1. If you flip them.
No. What do you have to do? Multiply them together, right? If you're adding 1/3 and 1/2, you just multiply the 2 and the 3 together, you get 6. There's your common denominator. If I put those two together, my common denominator would be cosine squared times sine squared. So that means you have to multiply the top and the bottom by what? So you wind up with, well, cosine squared, sine squared, over, oh, excuse me, plus cosine squared, sine squared, all over cosine squared, sine squared. which means you can break them apart because they have the same denominator. So you get sines. Oh, wait, I screwed something up here.
It would be 1.
Oh, sorry, I have this. Yeah, this is over a cosine. Yeah, like I said, I forgot this one. Just trying to scare you and I forgot it. I didn't do any homework over break. I'm sorry. I should have done this before I tried to show off and show you how scary these things are. I'm a jerk. I can do it. I just forgot how.
I got confused.
There's a lot of weird things that'll happen. I'm gonna give you 7 of these to try tonight. It's both. It's a combination of both of them. It's section 14.3. It's page 853, 28, 31, 37. The reason why I kind of cut through a lot of the different problems in this section is that there are other properties that deal with negative angles and half angles. I haven't quite, I haven't decided if we're going to do negative angles yet, or the, what do you call it, the cofunction ones. I don't think you have to worry about the cofunction ones because that's not, you don't see that even, I don't think you can do those in pre-calc. But we might do some negative angles here. It really isn't that bad. But I didn't give you any of those to worry about. Give those a shot. See how you come up with those. There's some simplify, some verify. They're not going to be horribly scary. Okay? They shouldn't be that scary.
What about that quiz we had before?